record. I'll record this. My call. Don't make this my call. I don't like that. I guess really for me, it's just like what is troubling you guys? Like what is the thing that for you guys is like stumping you? Must be struggling with Unit 3 personally. Which part of Unit 3? Part of counting and probability. Okay. So okay, got it. So counting and probability. So counting and probability. Is there anything specifically that in counting that I'm like looking at, or is it just like the concept in general? Mm-mm. Like which part of counting and probability am I like staring at? Just knowing which formulas to use in each question stuff me. Okay. So I think I have a Word document for this. Let me pull it up. Here it is. So think of it this way. We'll just copy this stuff and we'll just kind of like try to explain this. Okay. So the thing about counting that makes it tough is that it all depends on how you argue events. The thing that we have to teach you guys when it comes to counting is that there's not just one way to do like counting. I think the hardest thing is like you guys think that there's only one way to do it, but there's not. And how we approach a problem depends on how we argue some things. So the idea with counting is that we're using different types of events to help us determine what we can do with values. Basically these four operations of math, that being addition, subtraction, multiplication, and division, we can only use them depending on how you explain the scenario to us and how the scenario is worded. So, for example, let's say that we're trying to create goodie bags. This goodie bag is going to take in a bunch of candy. The idea is that it only takes one type of each candy, and there is no limit to how many types of candy we can have. So, for example, let's say that there are 6 types. There's chocolate, there's white chocolate, there's gobstoppers, there's nerds, there's caramel bars, and then there's Skittles. The only type of question we're going to ask when it comes to counting is just for you guys to find out how many possibilities there are. So for us, the question is how many different goodie bags can I make given whatever the conditions are? What's up? Well, it can't be 6 factorial because remember, it's not saying that you have to use every piece of candy. Because we don't know. Remember, we can have as much candy as we want in terms of the types. After that, we don't know. Does that make sense? So far so good on this stuff here. So let's try it. There's a lot of ways we can try to solve this. So let's try it with this method. I want you to imagine that there's a piece of chocolate. Okay. Now think of this. Now think of the chocolate and think of the goodie bag that you're supposed to put this chocolate that we have the chocolate in, right?
Okay.
What are the options for chocolate? What can I do with the chocolate?
Either we have it or not.
Yeah. The idea is that either you put the chocolate in the goodie bag or you don't put it in the goodie bag. So it's an on or off thing. But what about white chocolate?
It's the same.
And does that make sense? In fact, what about gobstoppers?
All of them.
All of them have that same option, right? They all have that on or off switch, right? So the idea is think about it this way then. Well, a goodie bag obviously could just have chocolate, right? And you could shut off every single other option.
I see.
So you could say chocolate, no white chocolate, no gobstoppers, no Skittles, et cetera, right?
So like the possibilities are like we either have like one of this and none of the others, or two of this and none of the others.
Like two of these types of these two
Yeah.
types of candies, or and none of the others, and so on and so forth. The idea is that it's just as reasonable to shut off everything but white chocolate. It's reasonable to shut off everything but chocolate and white chocolate, and the idea is with every one of them, right?
Okay.
So if that's the case, if it's just as reasonable to do all of those, notice in this scenario, whether we choose to put chocolate in the bag or not, there's no magic thing, there's no like magic force that's going to shove white chocolate in the box, right? So what kind of events are those called? If I know that picking chocolate does not impact how I put the white chocolate, what kind of events are those called? Not 6 choose 2. So think about it this way. There's
So is it 6 choose 1?
mm-mm,
There's a choose the end and being the types of candy.
yeah,
Uh,
that's the idea. Because what's happening here is because choosing the candy does not impact, or choosing Snickers or
Whatever candy is.
whatever the candy is, let's say it's chocolate, right? Choosing chocolate does not impact how I put the white chocolate.
Sure.
So then those events are what we call independent events. Independent events means the outcome of one event does not impact the outcome of a second event.
The dependency table for counting methods, how much does that cover? It's the four squares of.
Those are those are different types of problems where it's like indistinct items and indistinct categories.
Okay. Oh,
Those are
I-
different from these type of events.
Okay, what would this be if it was ordered? If it was like, rather than a
if
random bag, it was like a queue or something?
if it was like a queue, so like,
If order matters.
if order matters, then 6 factorial.
Okay,
Because when you put because there's a difference between putting Skittles
yeah,
and putting Snickers.
yeah,
So
and then putting them in versus another.
correct, yeah, so you're looking at a permutation, and permutations are technically defined with factorials.
Yeah. Okay, but why did you choose 2?
2 to the power, because remember, every option that we talked about, every candy had 2 options.
Oh.
And so there's 6 events where I'm saying 2 options. There's the event of white chocolate, the event of gobstoppers, the event of let's see, what else is there?
Caramel.
Caramel bars, Skittles, all those, right? There are 6 events that have a cardinality of 2, right?
Okay, yeah.
And because I said that those events are independent, all 6 of those 2s are being multiplied together to get us a total
So
of 2
2
to the 6, which is 64.
So if we had a problem where there was multiple different events per, well, you can't do that for candy, but like in that case, where it's just the cardinality of the possible.
Mhm.
Okay,
Yeah, so like the biggest thing I can say is when you're taking a big event that you're trying to calculate, you have to split it into sub events.
yeah,
The idea, for example, like how I did my card wrap, the poker wrap, when I identified a card, it's not that I'm just like picking a random card. You have to, like, for lack of a better terms, dissect what makes up a card. Just like how we can dissect the human body and identify the organs that make up a human body. Same thing with cards, goodie bags, everything and then everything in between. Does that make sense?
if we had this problem, and each candy was, each candy was rather like a set where it's like, you have the Laffy Taffy, then you have the blue Laffy Taffy, so each is 2. Is that now 3?
Well, so if you want to imagine it like that, so let's say you have Laffy Taffy, and then like now there's different types of Laffy Taffy.
Yeah, where there's 6 distinct sets, but each set contains 2 things.
Yeah, those now you have to take into account many ways can you do Laffy Taffy? Because now it's not so like when you jump into like the Laffy Taffy set,
Yeah.
now you're worried about, is there a blue? Which one am I picking? Am I picking the blue one?
Mm.
Am I picking pink, yellow,
Yeah.
orange? Those are all possible
How
sub
does it
events of the
change
event.
the behavior of the counting? Does it go to, it's
No,
a 2 to the
so-
end thing right now? Is it a 3 to the end thing, or does it change the behavior completely?
It completely changes depending on what your perspective is. So think of it like this. Think of it like a magnifying glass. So or like a laboratory scope. When you look at a laboratory scope, right?
Mhm.
Obviously there's the first level, but then you can zoom in. Isn't your perspective different when you zoom in? So you have to change your perspective
Okay,
on those events. Does that make sense?
yeah,
So like when we say, these types of events are disjoint, that doesn't necessarily mean the whole argument is a disjoint argument. It could be just that a subsection of your argument is disjoint. Does that make sense?
Okay,
So that's like kind of like how I kind of like approach that. It's like the hardest thing is that you need to keep your head on a swivel because it's all the perspectives are always changing
yeah,
when it comes to the problem.
can you itemize all the behaviors for
Yeah,
all the
we
counting
can-
stuff? But I mean, you have like, ordered, unordered.
Yeah, we can
like
item-
distinct and non-distinct, stuff like that.
Yeah, we can itemize like instead. So that actually kind of like leads me to another way that we could do without thinking of choices. So let's say for no apparent reason, the choices are unknown. Like maybe there was a choice I didn't account for, like eating the candy bar, eating half a candy bar, etc., right? So if I don't know what the choices are with a piece of candy, here's another way that I could think about it. So instead of thinking choices of each candy, think about the bag and the choices it has in terms of how much candy it can have in said bag. So up to how much candy can we have in a bag?
6.
6, right? Okay, there's six pieces of candy at maximum, right? Well, notice that I said the word at maximum, right? So you don't necessarily need to have 6,
You
in
might
fa-
have 5, 4, 3, 2.
or in this case, 0 as well, right? So up to 6 means that I can have 0, 1, 2, 3, 4, 5, or 6, right? Well, hopefully you agree, you can't have a bag that has 0 pieces of candy and then all of a sudden it has 6 pieces of candy. Again, there's no magic here, right? So now what you're noticing is that these events that I created, this type of perspective, is using what are called disjoint events because there's no overlap between them. Does that make sense? So I have literally created 2 different answers or 2 different techniques that uses 2 different types of events. Does that make sense?
Okay, but how would you get the 64?
How do we get the 64 from here? Well, because each of these scenarios, 0, 1, 2, 3, 4, 5, and 6, those are different types of events. 0 pieces of candy is an event, 1 pieces of candy is an event, 2, 3, 4, 5, and then 6.
Mhm.
Each of those events can be counted a certain number of ways.
Mhm.
We have to find all of those things, and because then they're disjoint, we have to add up all their cardinalities. Does that make sense?
So it'd be 6 plus.
So yeah, basically, right? So like think of it like this. So like if we have disjoint events, it's the fact that the sum rule tells us, hey, because your events cannot overlap, you have to add the cardinality of every single event that makes up, well, your big event, right? So for us, the big event of putting candy in a candy bag
Mhm.
is comprised of sub-events where you have 0 pieces of candy, 1 piece, 2 pieces, 3 pieces, 4, 5, and 6. Every single one of those events that I just listed has a cardinality associated with them. We're going to find all their cardinalities and then sum them together. Does that make sense?
Let me see.
Yeah, so no worries. So like what we're saying is that the total number of candy bags
6.
is well up to 6, right? But the total number of ways we can do like that event of doing up to 6 is given by the number of ways I can do 0 pieces, 1 piece, 2 piece, 3, right? So the idea is that we need to calculate every single one of these cardinalities. 0, 2, 3, 4, 5, 0, 1, 2, 3, 4, and 5, and 6. We're gonna have to find all their cardinalities.
How would you get 2?
So the question is, how did I, yeah, so that's the question. It's like, how did I get all these numbers?
Okay.
So let's
You
zoom.
can see the 6th one because it's like when we have 6
Mhm.
pieces, there's only one way we count it, and like when it's full, like the bag is full.
Yeah. So think of it like this. So with 0 pieces, how many ways can I take, if I have 6 pieces of candy and I need to take 0 of them, how many ways can I do that?
Or it's a series of n choose set or 6 choose n.
Exactly, right? This is what we call the choose formula. Because notice here, really, I said pieces of candy. I never specified which of the candies. So the question now becomes, well, which of these candies am I going to do? That is what we call a choose formula. The reason it's a choose formula is because the order in which I pick the items doesn't matter, because at the end of the day, a goodie bag is a goodie bag and it has candy, right? So for example, if I'm saying take out of 6 items, take 0 of them, there are 6 choose 0 or 1 way, we can do that because there's only 1 way you can take 0 items, which is don't take any items.
You're gonna take 1 piece, there's 6 options.
Correct, right?
So you have to- Okay.
That's why we have 6 ways, because if we only need to take 1 piece of candy, then there's any one of those six, right? Now, the question is, how did I get 2, 3, 4, 5,
Okay,
and then
for
for
two,
six?
then we have to, we can take these two, this is one way, and then these two,
Mhm.
this is one way, two.
Yeah, so what you're noticing is there's quite a few.
You're counting with my fingers, that's why it's a two of the.
Oh.
Yeah,
You can see.
so here's how we can word this. So you guys are CS majors, or at least have taken a programming class before. So think of it this way. Here is a 2-person string. There's a two character string, okay?
Okay,
And you know that there's for a 2-character string, there's 2 pieces of candy. My question or there's this, there's 2 spots you need to fill up with your 6 pieces of candy.
Okay.
My first question is this: how many choices does that first spot have?
6,
The second guy?
6.
Are you sure? Remember, 5, because we
yeah.
can't have duplicates of
Okay,
a piece of candy.
Mm.
So do you agree that choosing the first candy does not invalidate any other piece of candy? So if I say chocolate first, does that all of a sudden mean white chocolate gets off the board? No, right?
Just take chocolate itself.
Yeah, it just takes chocolate itself, which is fine, right? So what we can argue is that choosing the types of candy is what we call semi-independent, because even though like there is like a dependency that we can argue, what I'm arguing is that that dependency is so negligible since it leads to the same outcome, which is having 2 pieces of candy in a bag.
Okay.
Does that make sense?
Yeah,
So notice, not only within this disjoint event disjoint argument I'm trying to make, I'm also making an independence argument. That's what I mean by that laboratory analogy, that lab scope analogy, is by I'm zooming into a specific scenario and I'm having to argue that scenario is something entirely different than the big argument that I'm trying to make. Does that make more sense? So we have that independence behaviors. And so because there's independence behaviors, 6 times 5, 30. Nothing crazy about that, right?
but we cannot take all the.
We can't do all 30 options because the problem is this. What if let's imagine I took gobstoppers and nerds. Again, I just said that order doesn't matter, correct?
Mhm.
Well, for me, gobstoppers and nerds is the same thing as nerds and gobstoppers. The problem was that 30 counted that 2 separate times. Does that make sense? This is what you're noticing is that this is a typical process in counting, simply known as overcounting. Basically, we counted an event too many times, or in this case, we counted all our different types of events too many times. So we're going to need to get rid of them. So to get rid of overcounting, the easiest way to do that is by doing what is called the division rule. The division rule says that if you have a total number of events and each type of event is being counted k times, divide your answer by k factorial.
So it will be 30 divided by.
How many times do we count each type of event? So like when you take 2 pieces of candy, right? When you have 2 pieces of candy, think of it like this. Now, when we have 30 pieces of candy, right? Or 2 pieces of candy,
Because
correct. Now, this is what we call 2 factorial. The reason why it's 2 factorial is because you're trying to what is called descramble the order of the candy, because again, order doesn't matter. So when we descramble it, we get 2 factorial ways, or just 2. When we divide 30 by 2, we get the answer of 15. And now you wash, rinse, and repeat
so
for every single one of them.
3 would be.
So,
Would be 6 times 5 times 4.
and
Divided by 3 factorial.
exactly, and that's 20.
That's
5 times 4,
30 times 4,
120, and then divided by 3 factorial.
which is not.
3 factorial, no, 3 factorial 6. 3 times, remember, factorial is 3 times 2 times 1
So 120 times divided by 6.
is. Isn't that what I got there? Wash, rinse, and repeat for literally every single one of them. Once we get all 6 of these values, sum them up together, because remember, The overarching argument that I made is that all these types of events, 0 pieces, 1 pieces, 2, 3, 4, 5, and 6, they have to be disjoint from each other because there's no way I can have different amounts of candy in a bag. Does that make sense?
So how does the overcount apply?
The overcount applies within the sub-event of a specific scenario. So for example, in 2 pieces, right? The problem is there's an overcount within the 2 pieces because you can reverse the order in which you took the items. And they're still the same. You grab the same 2 items, right? So so the overcounting is not happening within the within the sum of these guys. The overcounting is happening when you're trying to count each of the sub events. Does that make more sense?
Yeah,
That's why the analogy of the lab scope is what I'm making. The lab scope tells you to zoom in and zoom out as necessary. Notice that I'm zooming really far into this problem because I'm not focusing on the overarching event. I'm just focused on a specific part of the human body. Make sense? In this case, 2 pieces of candy. Just like how I would have done the same thing if I zoomed in on 3 pieces of candy. That has an overcounting problem. So does 4, so does 5, and so does 6. Does that make more sense?
Then we just add all of them.
We add all of them together because they're all disjoint. And so if we add them all together, guess what? You still get 64. So I just gave you 2 types of the same problem solved in 2 different ways. That's the whole point of counting. The whole point of counting is that there's multiple techniques in which we can approach a problem. It just depends on how you argue that problem to us. Does that make more sense? Yeah. Yeah, that's all it is, the counting. Basically, it's just you need to identify when to use the 4 mathematical operations, identify the relationship between events, and then do math. The hardest part is just making sure you keep your head on a swivel. Zooming in and out is the hard part. Make sense? So as an example, let's see if you guys can try this. So example question. There is a pizza shop, and this pizza shop allows us to put at most, let's say, 2 toppings on our pizza. Now, there are 5 toppings. How many pizzas can I make? Nope. So think of it this way.
There's 5 choose 2.
Well, is it just 5 choose 2?
Oh, plus the cases where it's 1, plus the case where it's none.
Exactly. There are three situations we need to worry about. There's 3 situations we need to worry about. A pizza with 0 toppings, a pizza with 1 topping, and then finally the pizza with 2 toppings. You need to count all the ways that you can do these 3 sub-events, and then the argument that we can make is that these guys have to be disjoint from each other, because there's no way you can make a pizza that has 1 topping and 2 topping. Does that make sense? That's the basic idea.
Because there's 5 toppings, almost 2. Does that mean like, where is like the overcounting?
The overcounting comes with, for example, with the pizza with 2 toppings. So when you think of 2 toppings, right? Let's say I have sausage and pepperoni. Does the order in which I put the toppings on matter?
No.
No, right? But then I could just have easily said, instead of sausage pepperoni, do pepperoni sausage. There's no difference. It's the same pizza. But the problem is that would have counted twice, which we need to take into account. I think like off the top of my head, this would have been 5 choose 2 right here, whatever that is. I think that, yeah, that I think that's 10. 5 choose 2, which is 10. Yeah, and then 5 choose 1, and then 5 choose 0, which is 1. And then just 1. So add those 3 guys up together, we get 16 different pizzas. Make sense? That's the idea with that. Pretty straightforward. The overcounting is already taken care of when we say 5 choose 2. When I say 5 choose 2, that immediately takes care of overcounting. Yep.
What is it, it's like, you're gonna have the same topics,
What's up?
like if you have 5 different topics, but you're gonna have the same topics.
If you have 5 toppings, but you can't have the same topping,
Like, like, can I have cheese and cheese, but you have to choose something else for that.
what, so what are my toppings that I have?
Say, cheese, olives, chicken, and beef.
So chicken, olives, pepperoni, what else?
Beef,
Beef, cheese, okay. Yeah, we'll say these 5, right? So once you use a topping, this is assuming that you can't use it again.
Yeah.
If we allow for repeats, then that makes it harder because when you do the 2 toppings, right? How many options does the first guy have? Are you sure? So your first topping, how many choices would you have had?
5,
And then the second choice?
4.
Nope, not if you allow repeats.
Oh, if you allow repeats, that's another 5.
So does the first topping impact the second topping? No, so how many total pizzas could I have made in that case? That's why there's a massive difference when we say allow repeats or don't allow repeats. Technically nothing here, I think. agrees.
You count repeat, right?
What's up?
This question we allow repeat, that's why we get.
No, I think it's over.
What's up? Wait, say that one more time. Sorry.
Over here, you choose, like, we can repeat the,
No, you cannot repeat the toppings.
over here we can.
Yeah, no, you can't repeat the
If you
toppings.
can't repeat the toppings, how does it change the behavior? So if you can't repeat them, we have this choose behavior.
So now out of those, so now we know that you have to choose 2 toppings. Now you actually need to tell us like which of those toppings you're taking, like the topping combinations,
Yeah.
of which there's 25 topping combinations. Hopefully choosing the toppings doesn't impact the topping combination. So like we will get like 250 pizzas that are brand new or something along those lines. Does that make sense? Because like what happens is that you would need to tell us how many so you would need to tell us here are your toppings, now make the pizza,
Yeah,
right? So now on that pizza, how many ways could you make that pizza?
25, which I have repeat.
Yeah, that's the idea.
But if I cannot repeat it.
Just 5 choose 2. Because you just throw them on the pizza and you're done. Does that make no sense? Yeah, what's up?
So you don't, if you want it like overcount.
If you repeat it, that you could have some overcounting, depends on what the argument is. Doesn't mean. If you have overcount, if you do repeat toppings, so like sausage,
Like, let's say you do like sausage starting and then like next week you have like sausage.
that's the same thing.
Yeah.
But like, no, that's an overcounting, but when I mean double toppings, I mean like sausage.
Okay.
Sausage, that's a repeat. So like repeat means like you literally pick the same topping twice. Right? And I guess apparently sausage is just different from regular sausage. in
What
some
if
bits.
order is like important?
What if order is important? Then it's a 5 factorial essential. It would be 5 times 4. Because when you do the first topping, you can tell the difference between pepperoni and sausage.
Yeah.
So for us, if order does not matter, pepperoni sausage is not equivalent to sausage pepperoni. So that means those 2 should be counted as a different answer.
That would be an factorial thing.
That is a factorial thing.
So what if
More or less.
repeats were allowed and you had the same thing? What would it be then?
What do you mean? Same thing?
So if repeats aren't allowed, you have the n factorial, you kind of with n factorial, right?
Mhm.
If repeats are allowed, how does that change the way that, or how does that change like the counting method?
I mean, it's still the same. You're still using the same event. You're still using the type of events. You just have to argue in a different perspective. So like, let's say that there's repeats. So like, are we saying like if we're saying that there are repeats, so like we could say sausage. So like you could say like sausage or something like that, right? What happens is that when you do you have to do this 5 different times because there's those 5 in order as well as the different combinations. Right?
Oh, so it doesn't change the counting method, it's just kind of a asterisk that makes us have to think and we go +5.
Plus like another however many combinations you need, right?
Okay.
So that's what we need to take into account.
You want to go over some of the questions on the practice?
Sure. Which one am I?
15 to 16. Oh, so those are like counseling, or like they're not-
We can take a look at those. So, so this one here is basically as follows. What we have was, so it's this one, right? All right, let's try this. All right, so this is one of those questions that's just really annoying. Try not to calculate this, but we'll figure it out later. All right, so there's 10 distinct people there's 10 people that need to be ferried across the river. Now there's a boat and there's a captain on that boat. The captain says that you can put only at most 2 people on said boat. And apparently, according to said captain, how you order the people on the boat, notice I'm saying the word on the boat, does not matter. And assume that it's a one-way trip, which is god awful. But assuming it's a one-way trip and all this, we need to figure out the number of ways we can get the people across the river. Okay. All right. So let's start it like this. So let's try this. So, all right. Now, how many people are there? Good. All right. So there's 10 people. And now, up to how many people can be on a boat? Yeah, right? But notice it's the word up to. It's not exactly.
So it could be 1 or 2 or 3.
Yeah, so it could be 2. So in reality, the number of people on the boat could be 2, 1, or 0, right? Now, assuming that this captain wants to go home, probably is not the best thing to do if we say no one's on that boat, right? So we're going to chop off that part. Yeah, because there's no way the captain will ever stop taking trips, which seems reasonable. All right, now the number of people that's on the boat is either 2 or 1. Now the question is this. So now the question is this. What is the smallest amount of trips the captain can take? 5. It has to be 5 because this is where, yeah, he carries 2 people every single time, right? What's the maximum? 10. He carries 1 person every time, right? But he doesn't need to do 5 or 10, right? In fact, there's a range of values. Up to how many, what are the possible number of trips that this captain can take? Are you sure it's just 10 or 5?
Oh, he can do between 10.
He can do between 10 and 5. And that's the key important part. He can do 5 trips. And we need to count every single one of them. Every single one of them has an associated value attached to them. So you could have 8 trips here, then obviously 9 trips, and then finally the 10 trips.
That's what 1 person is.
No, it's like.
For the 10 trips, yeah, that would be with 1 person every single time. Now, the thing is, these are all like really tough to calculate. And so we're going to have to figure out a method to do this. So let's zoom in on the 5 trips. If we zoom in on the 5 trips, so let's zoom in on this 5 trips. How many, so my question is this. How many trips are there in total? Here. Yeah, just 5. Now, how many of these 5 trips carry 2 people? All of them, right? Yeah, all of them. How many ways can we choose 5 trips out of 5 to carry 2 people? Are you sure? It's like saying this, there's 5 trips, you need to use all 5 of them to carry 2 people. Only one way. You can't, there's no other way we can do it. We have to have them all take that trip. Does that make sense? Now, we know that all 5 trips, right? All 5 trips have to carry 2 people. Now, who goes where? The question is now who gets to go on which trip?
Is every person considered distinct?
Yeah, you can tell the difference between them.
Okay,
so-
So that counts as a different way, depending on how you arrange them.
Correct. Depending on how you throw the people on their respective trips, that, for example, person one going on trip one is different from person two going on trip one, and so on and so forth. Does that make sense? So now we need to figure out how to distribute the people amongst the trips, right? Well, think of it like this. So how many options does the captain have for his first passenger? Not necessarily 10 choose 2. Would you agree that there's only 10 options for the first guy? So because remember, we're just saying, hey, you go first, you go second, you go third, blah 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 blah, and so on and so forth. We'll group them in a bit later. We'll take Yeah, this would become a 10 factorial because it would be the second passenger would be 9 ... all the way to the final spot, which is 1. So now we have 10 factorial ways. Does that make sense? Now, the problem is this. Now the 10 factorial says, hey, I know who's going where. But remember, there's an order in the boat. Or for lack of a better terms, lack of order in the boat. So let's draw this out. Let's show this situation out here. Here is my boat. It is a bad boat, but it'll work nonetheless. Let's say that there is person A and there's person B right here. What do we know about the order in the boat? Doesn't matter, right? So if I seat A and B here, does it matter if I swap their order? No, right? Right? These guys can swap around. Well, the problem is that 10 factorial counted this twice. Do we have to subtract?
Would we divide by 2?
We would need to divide by 2, right? So remember, so the idea is that, so now each boat, so the first boat can be descrambled, basically, sorry. Yeah, so it would be descrambled with 2 factorial ways, right? Because there's 2 ways you can reshuffle that boat. But notice that I said the first boat. How many boats are there? There's 5 of those boats. And what do you think I'm going to say about all 5 of those boats? If the first boat had a problem of orders, all of them have a problem of order. So guess what? The second boat is also descrambled. So technically, so think of it this way. So we need to divide out by how many ways we can essentially descramble the entire event. Yeah.
Would it be better to write it as like 2 factorial?
Yeah, so in total, right? So in total, there are essentially 2 factorial ways to the 5th way, ways that we can descramble all 5 boats. Does that make sense? The descrambling means that now the order in the boat no longer matters, which is what we want. So now we have this 10 factorial. Now we just take our 10 factorial and divide by the number of ways to descramble, giving us a total of 10 factorial divided by 2 factorial raised to the 5th.
Is that the same thing as 2 factorial times 5 factorial?
No, so it's just 2 factorial times 2 factorial times 2 factorial. It's literally just saying 2 factorial 5 times and multiplying them together. Yeah, basically 2 to the 5th. But guess what? That was only for 5 trips. Now you got to do it for 6 trips. So first, remember, we need to decide, we need to know how many of these boats are carrying 2 people. Because there's 6 trips, you don't know which of those boats are carrying 2 people. There's 4, yeah, out of 6 trips, right? This would definitely be a hard problem. there's no way that this isn't a quick problem. So out of 6 trips, 4 of them would be need 2 people, right? The question is, how many ways can we choose those 4 trips? Nope. My question is, I know that 6 out of 6 trips, 4 of them need to carry 2 people. Is it the first, the second, the third, the fourth, the fifth, the sixth? Which of them? It is a 6 choose 4. That's correct. Yeah. There's 6 choose 4 different ways that we can choose which of the 4 trips have 2 people in them.
Well, why is it for?
Because think about it this way, there's 10 people, right? So you would agree 10 people, right? Now, 10 has to equal 2x plus like 1y, right? Where x and y, x is the number of 2 people trips, and y is the number of 2 people trips, or one person trips. How many? So my question is this: if you're trying to say that 10 is equal to 2x plus 1y, and we need to find what x and y is, well, how many of those trips are carrying 1 person? Or is it all 10 of those? Is it all 10 of those people? How many of them need to go on their own little adventure? Out of 10 people, right? Only 2 of them need to go on their own little adventure. So that tells me that this is 2. And what does that? And so if 10 is equal to 2 plus 2x, 2x is equal to 8, telling me that there are 4 trips that need to have 2 people in them. Does that make sense? That's where the 4 came from. And so now we have this. So now we have this guy here. So now we chose which of the 4 trips have 2 people in them. Now you got to distribute the people. Now distribute the people. So now, do you agree that there's 10 factorial ways to create an order, right? That 10 factorial is saying, hey, person 1, you get this guy, person 2, you get this number, and so on and so forth. Does that make sense so far? Similar to how we did it. And just like last time, right? We need to divide. I'll post it as well. But we need to divide by how many ways we can descramble the boats. And in this case, the ones that we need to descramble are the boats with 2 people in it, not the boats with 1 person. So how many boats have 4 people in it? Or how many boats have 2 people in it? 4 of them, right? So we need to descramble. So we need to descramble the 4 boats with 2 people in them. Exactly. That's given by 2 factorial to the 4. The first boat has 2 factorial ways we can descramble, then the second, then the third, and then the fourth.
This I keep going down, like.
Ding, 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 ding. Yeah, there's a pattern. Yeah, the pattern picks up very fast.
All of them divided by that number.
What's up? Yeah, so 10, so you would have 10 factorial divided by 2 factorial to the 4th. But that only tells us the people. That only tells us how to complete the shifting. But now we had that 6 choose 4, right? So does picking which of the boats have 2 people in it impact how I do the order?
No.
No. So what I need to do is I need to multiply this value by 6 choose 4. The reason I multiply by 6 choose 4 is completing the trip is comprised of 2 parts. Telling the captain which of his trips are going to be 2 people in them, and then actually giving him his orders.
Okay, don't we have to add?
You do have to add of every single one.
No, like, the number of votes, like, we have 1 person,
What's up?
like, then we have to add the number of votes where, like, we have only 1 person.
Well, that would be in the descrambling part here. But even if I do that, how many ways can you descramble a boat with 1 person in it? 1 factorial, right? Well, what's 1 factorial? So why put it in there to begin with? That's why it doesn't matter.
But it can affect the 7 here.
You gotta do, and now you gotta repeat this for every single one of the remaining 4 trips.
Seven.
Then add them all together.
I'm gonna do it multiply that. I'm gonna do it multiply by 6. Multiply that by 6 choose 5.
Because how many, well, because we would have needed to multiply here by 5 choose 5. Because for us, this is 5 choose 5. Out of 5 trips, you need to take all 5 of them to carry 2 people, of which there's only one way, right? Well, what happens when I multiply something by 1? That's why I don't multiply. There's no reason to. Technically, I could say that, yeah, this is times, if I wanted to keep the pattern, this would have been 5 choose 5,
So
but that's the same thing.
for 7, it would be 10 factorial over 2, 3 times 7 times 3.
Bingo. Yep. That's it. That's basically what it is.
But now we have to multiply by 3 factorial,
Why by 3 factorial?
because those are the number of people we have, like 1.
No, those are, so those 3 people, there's nothing we need to descramble with those the only thing you need to worry about is how many ways you can descramble the boat with 1 person. But there's only one way you can descramble it, so it doesn't matter. Does that make sense? The only thing that matters is the 2-person trip. That's where problems start occurring.
So for the second, that's the like amount of ways people could go and on, right?
Which that is the number of ways the captain gets his orders of knowing which of the 7 trips carries 2 people.
Got it, and then the one factorial ten over two factorial, that's the amount of weight for each person.
That is throwing the people on the boat. Yeah, so throwing people on the boat times how many ways can I get the orders to carry 2 people? Essentially, and you're just repeating that over and over for 8, 9, and 10.
We have to add all of them.
And you have to add all of them together because all of these events that we created, 5 trips, 6 trips, 7, 8, 9, 10, they're all disjoint from each other. So the total number of ways that I'm looking for is the sum of them.
You get to see like the final.
Please do. This is way too giant. The total answer is the sum of all these cardinalities.
We can just leave it as that plus that.
Yeah, you don't simplify that. God, no, please never simplify that. Yeah, does that make sense?
Yeah.
Yeah, so that's the idea with 15. Or
16.
what's 16? This one? Sure. So, alright, so.
From the bottom.
It says at least 3. Fuck it.
Before you move on.
Sure, what's up?
You have a list of distinct elements, if order matters, the way you can, it's n factorial. The way you can arrange it.
Yeah.
And if order does not matter, you get the length of the amount of elements, choose the length of the list.
Choose the length of,
So if
yeah, choose the length of the list, yeah.
Okay. got it.
Or the length of the list, choose how much you need, essentially. Because like if
Oh, I
you,
see.
because like think of it like a string. Like if it's an 11-person string and only 4 of them are like
Yeah.
need to be A's, then it's just 11 choose 4 for where the A's go.
If you have 11 people and 4 of them are standing in a line, it's 11
Choose
choose 4
four.
for how many ways they can stand.
Yeah.
Okay, got it.
Because order doesn't matter. If order doesn't matter, then it's 11 choose 4. If order does matter, 11 times 10 times 9 times
How do
8.
you do order does matter on a shortened list?
On a short list, you just need to figure out, so like, let's say,
Before with n factorial over the length of the list factorial.
no, it's basically like if that's your list,
Mhm.
right, and you have 11 people, the first spot has 11, then 10, then 9, then 8.
Mhm.
Everything, you multiply those values together and that's it. Because order does matter. Every single permutation,
Yeah.
everything I do, every new order I give is a different order.
If you have the same thing as last time, you have 10 people and a order does matter, line of 4.
And just, order does matter, 10 times 9 times 8 times 7.
Okay, 10 factorial over
4
10 minus 4 factorial, 6 factorial,
10 factorial over 6 factorial, yeah,
okay,
more or less. But that's just like some stupid math, but yeah, 10 times 9 times 8 times 7, essentially. The 10 factorial over 4 factorial is just a nicer way of putting it rather than writing that. That makes sense? Oh, wait, so I think it's this thing right here, right? The 535 indistinct delegate positions. that's given amongst to 50 distinct territories. And every territory needs to get at least 3 positions, right? Okay, well. Is there a difference between the positions?
Yeah.
No, yeah, there's no difference between them. No, right? They're all indistinct, meaning they look all identical. Is there a difference between the territories?
Yes, yes.
There is a difference between the territories. There's 50 of them, and it's basically territories. And we are distributing, right? We are distributing the indistinct items amongst distinct categories. Does this sound familiar to you? What kind of? Yeah.
Since every territory gets 3 positions and
Mhm.
positions are distinct, and we just like 50 times 3 and then kind of like cut that section out.
Yeah, that's exactly what we need to do. And so this is a stars and bars problem, but stars and bars, but we need to get rid of the restriction.
When do you determine when you use stars and bars?
Indistinct items being this, if you have items being distributed into categories, but the items are indistinct and your categories are distinct. So first we need to get rid of this condition. So the condition is that every territory needs at least 3 positions. So how many positions are used up immediately? If every territory needs at least 3 positions, 150, right? Right? So that leaves us with essentially 535 minus 150, which equals 385 remaining spots that we can distribute freely amongst the 50 territories. And that's where stars and bars comes in. This is where we use stars and bars now. Does that make sense? So our formula, our answer would be 385 plus 50 minus 1, choose 50 minus 1. That's all we need for that. The minus 1 is because the stars and bars is n plus k minus 1, choose k minus 1.
Oh.
So
What do I just plug in?
Leave it that way, and that's okay.
Yeah, because we don't give you a calculator unless you want to try to calculate what this spits out.
Great.
Yep,
That's just like a straight.
straight up. Yeah, pretty straightforward.
It's on the formulation.
Yeah, stars and bars. Mhm.
stars and bars is on the.
I think so. I want to say yes. I'll double check though. The 50 minus 1 is because the stars and bar. Oh, 385. This is following the formula. That's following it's following the formula. It's
385 remaining spots and then 50 is the
Yeah.
territories.
so where n is the items, and k is the categories.
Yeah.
Yep. Pretty straightforward. I could also do choose n. Doesn't matter which one. Yeah. Yeah.
The ones that.
Mhm.
Multiply the 50 times 50, that's.
Yeah, 50 times 3 is 150. The reason why I did that is because you need to get, in order to use stars and bars, you need to knock off the condition that every territory needs at least 3 positions. Because remember, every territory needs at least 3 positions. So the idea is, in order to use stars and bars freely without worry of the formula, knock off the condition first and then subtract that from how many total items you have.
Since the calendar conditions are in this, you can just subtract the ones that are.
Yeah.
Because each one needs 3,
Exactly.
so it doesn't matter which one gets given to which one, it's just get rid of it.
You just get rid of the 150 items.
Is it always that indistinct is n, distinct k?
Yes, always for stars and bars. That's the only time you can use stars and bars is when n is indistinct.
Can we do 18 and 19?
What is 18 and 19? Says. What is the chances that at least 3 of them are playing? Okay. So. Okay. So let's try to explain this. So. Okay. So you grab a bagel with an infinite number of bagels. There's twice as many plain bagels as one of the poppy seeds. Randomly, we're just going to grab 10 of them. We need to know that the chances, what we need to know the chance that at least 3 of them are playing. Okay. So think of it, what we're going to apply is what's called this. So do you agree that at least 3 and less than 3 are polar opposites? Meaning that, think of it this way, it's kind of like saying that raining and not raining is not the opposite, right? Because like when we say at least 3, the opposite of saying at least is less than 3, because it can't be greater and it can't be equal, so it's exclusively less than. So what we're gonna say is that, so what we can say is that the probability of at least 3 plus the probability of less than 3 has to equal 1. These are what we call disjoint probabilities. Remember, with disjoint stuff, we add them together. And in this case, we get the total probability of our universe happening. It's either that you have to be greater than or equal to 3 or less than 3. We're making it a black and white conversation, essentially. Does that make sense?
Yeah.
So to make, we're using the sum rule, or the sum rule for probability. The probability of at least 3 plus the probability that it's less than 3 is equal to 1. Does that make sense?
So yeah, basically equals like.
The event plus the reverse of that event has to equal 1 because it's a black and white thing. Just like how a total, like the total number of ways we can do the event, today's event is,
Always in the opposite.
yeah, either studying or not studying, like they have to be polar opposites. That's why I mentioned like the polar opposites thing. So the thing that we're trying to find is the at least 3, right? Which is 1 minus the probability of less than 3, right? And so now we need to figure out what is the probability that we're going to get less than 3 things, right? All right, so now the probability, that we get less than 3. Well, if it's less than 3, what are our options? What are the options that we have for that?
2, 0,
2, 1, and 0, right? If it's less than 3, there are 3 situations that we need to account for. Probability that we get 0, probability we get 1, and the probability that we get 2. Each one of them we need to find. Does that make sense?
Yes.
Now, think of it this way. If you have at least 3 of them, right? So what is the probability? What's the probability that you get a plain bagel?
So poppy seeds is twice as. I'm saying 33%.
There's twice as many plain bagels as poppy seeds.
Well, the chance of getting a plain bagel plus the chance of getting poppy seeds equal 1.
Yeah.
And since poppy seeds. Oh, there's twice as many plain bagels. Okay, so. Like, yeah.
2/3 or 66, and the probability of getting a poppy seeds has to be 1/3, right? So we're trying to get so we would have 0 plain here. This would be 0 plain, then 1, and then the last guy we need to do is 2. Does that make sense? And so now we need to figure out what these probabilities are. Well, okay. What's the probability that you draw 0 plain bagels, 0 plain bagels? Nope.
It's 2.
Nope.
2.
What's the chance that, so if you get 0 plain bagels, what is that the same thing as saying?
I'm
And
assuming
choose.
you get poppy every time.
You
so
need to-
1/3 to the power of 10.
Ding, 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 ding. Yeah, this is just 1/3 raised to the power of 10, because this is the same thing as saying that instead of drawing 0 plain bagels, every time I drew a bagel, I drew a poppy seed bagel.
I'm
And-
assuming,
Mhm.
I'm assuming the power continues to be 1/3 to the power of 9. 1/3 to the power of 8.
Well, that would take care of, so you have, so couple things, yeah. So there's this 1/3 9, and there's these 1/3 to 8, but that only takes care of the amount of bagels that are poppy seeds. The problem is, not all of them are poppy seeds. Some of them are actually plain. So what is the chance I'm going to get a plain bagel?
So it would be times 2/3 to the power of
Mhm,
times 2/3 to the power of 8.
exactly. And now, this seems reasonable, except there's just one more problem. Where did we draw the bagels? Did we draw the poppy seed first? Did we draw the plain first? Where did we draw, what position did they come in? It does matter. It does matter where they're coming from. Because there needs to be, well, it doesn't matter, but like, so then if it does, well, okay, so if the order doesn't matter, right? Then you need to know, then we need to know where the position is. Like, we need to know where specifically we're putting it. Are we getting it when we drew first, second, third, fourth, et cetera, right? So how many ways can I pick 1 plain bagel out of 10? How many ways can I choose that? Yeah, 10 ways, or really 10 choose one. Because out of 10 bagels, we would have 10 out of 10 bagels, one of them needs to be a plain bagel. And there's 10 ways to do that. What about with 2 plain bagels? Ding, 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 ding. And so now we have all these values here. Yeah, I'll post this, see that. Yeah, so now we have them. Yeah, now we add them, right? So the probability is equal to just these guys. Why does the index of the selection matter? Because we don't know where specifically we're doing it. We need to know specifically where, when we drew it. Is y. So we would have this plus probability of this. Yeah, what's up?
But for 0 plain and we can choose 0, and that should have 1.
Exactly, which is why I didn't put it up there. Reason why order matters is, or why the index selection, bagel selections matters is that, yeah, we need to know when it's a single.
Why did you multiply by 2 over 3?
Because that's the probability that you get a poppy seed bagel.
And the 10 choose 1.
Oh, no, sorry, that's the probability that, so 1/3 is the probability you get a plain, 2/3 is the probability that you get a poppy.
No.
Is it? Motherfucker, motherfucker, I hate this. Whoops. Okay. Hold on. I might have just reversed every single number. Yeah.
2/3 to the power of 9.
Yeah, that should be 2 to the power of 9, I think. Wait, no, this is right.
Yes.
No, I'm good.
I was
Okay.
wondering what you meant, you just mixed up the words.
I just mixed up words. God, I hate English. Yeah, so this is fine. This is fine. The probability that you get a poppy seed. Because remember, there's twice as many points as.
So I'm assuming the probability of getting at least 3 is 1 minus that entire equation.
Yeah.
Okay.
10 choose 3? No, there's no 10 choose 3 because you don't need to account for a situation where there's a 3-point bagel. No need for 10 choose 3 when there's not an option for 3-point bagels. Yeah, only less than, not less than or equal to.
Continue until what? Here?
Probably to like 5.
5.
Let's say around
Okay,
5.
I'm gonna believe you.
Okay, fun. How do I get the 1/3 and the 2/3? The fact that there's twice as many plain bagels as there are with poppy seeds. And so the chances that you draw at least 3 plain bagel, the chance that you draw a plain bagel has to be 1/3. or 2/3, sorry. Because this would be like 2x plus x or 2x plus y, and so there's a total of like 3 essentially. Any questions on that? Yeah, what's up? Yeah, what's up?
Probability that you draw zero tables. Shouldn't it be multiplied by 10?
Wait, say that one more time.
For this, for probability that you draw one plane, zero plane.
Okay.
Shouldn't it be multiplied by 10?
No, not multiplied by 10 because there's not 10 ways to get one. Yeah, it would be 10 choose 0,
Yeah.
but 10 choose 0 is just 1. 10 choose 1 is the 10. Yeah, so 10 choose 1 meaning 10 different positions to pick the 1 point bagel. And then 1/3 because on that spot, the probability that it's a bagel is a plain bagel is or the probability that on a specific spot the bagel is a plain bagel is 2/3, and then poppy seed has to be 1/3. The only thing that matters order wise is when you get the where we get plain bagels, pretty much, or yeah, more or less, because we need to consider where it's happening since they all fall under the same situation. Any questions on that one? Cool. All right, let's try the question. This one. All right, so this is like one of the this is an example of just regular straight up probability. So there's a test that detects if someone is human. This test has a 90% success rate that's independent of the participant being a human or a computer. 95% of the participants are going to be human, and the test is going to tell us that my friend that they are a computer. Given all this information, what is the chance that my friend is actually a goddamn computer? So this is going to be a headache and a half. Let's figure out how we can try. How did I do that? Okay, so what is the probability? How much of the participants are computers? Let's figure that out. How many percent of the participants are like actual computers? Only 5%. Yeah. That's a regular Now, so what our goal is to find the chance that or find the chance my friend is a computer given the test said that my friend is a computer. Does that make sense? So in other words, we're trying to find the probability that my friend is a computer given the computer the test says computer. Does that make sense? That is what we are trying to find. It's the cop, it's the speeding problem essentially. It's literally just a carbon copy of the speeding problem, and we're gonna have to figure out a bunch of numbers. And so what happens is kind of like this. The problem. So, what do we know? What information do we know? Okay, so we know P. So the probability of computer is what?
90.
Is it 90%? How many?
It's 5.
Only 5%. Yeah, so 0.05. What's the probability that this person is that we have a human?
0.95.
Now, there's another thing, there's something else we know. How do we interpret the 90% success rate? There's a 10% error, but how would I write this in terms of probability?
10% of 0.95.
So like probability of what is equal to 0.9?
Probably. You're a human and the test is.
Probably the computer is right.
Yeah, the probability that, yeah, so how we say it is that the test says human, given that you're human, the probability that the test says human is 90%, because it's supposed to be 90% accurate. And so if we have the probability of, if we know that, what's the probability of this guy here? The same thing, right? So now we need to figure out this. All right, so now what is this formula? What is this formula essentially? What do I need for this formula? What's up? So what's the definition of conditional probability?
Intersection.
Okay, the computer and so the computer intersection with test, or I'll just say test computer divided by what?
Probability of
All right, cool. Now we need to find out both of these guys, right? So let's figure out what this is. What is the numerator? What's that numerator? Oh, oops, this is test computer. Yeah, the numerator. What's that probability? So remember, we know that the test has a 90% success rate independent of the participant being human or computer. So what do we know about these two events here? Is it 90% chance? 90% chance would say the test screams human, but I want to find a chance that I'm a computer and the test screams computer.
The event test computer, what is that?
What's up?
The event test computer, what is that, right?
Yeah.
0.99.25.
Correct. So because what's happening is that these probabilities, they cannot impact each other. Remember, it's the test success rate is independent of this oops, so it's independent of this, right? So let's see here.
So the probabilities are.
Oh, sorry. Yeah. You're good. No, keep going.
Yeah, so the probabilities are independent, and you can multiply them to get the one probability.
Yeah, we can multiply them together because they're independent events. So the probability that we get a computer times the probability that the test is correct, essentially. So like, let's see here. Is that what I wanted to say? Probability. Yeah. Which is screaming that this test is correct. Okay. So we want to say the probability of test computer. Test screams computer, given that you're a computer. That's fine. Okay. So what is this probability? What do we know about this? Is there anything we know about these probabilities here? Also the reason, you should say that the probability of test screams computer has to equal the probability of the test computer. I think. Is that what I want to say? Yeah. So, so what is the probability that we get the probability that the test screams computer? Because so we have the probability of computer and test computer, right? And what's happening is that this test always has a 90% success rate regardless of what the participant is. So whether or not this test screen, whether or not you're a computer or not, that should not impact whether the test, if you're a computer, that's independent of screen, that does not impact whether the test screams computer. So like it can't tell the difference essentially. So what's happening is that the probability that the test screams computer is equal to the probability that the test screams computer is the probability of the success rate, whatever that is. We'll just say what the probability of the success rate. Kind of hate it. So yeah. Let's see. There's like a
Wouldn't that be divided by the probability that they computer?
which one?
Last side.
This guy here?
Yeah.
No, this is given that. This is given that. So given that I'm a computer, what's the chance that the test is going to screen computer at me? Yeah, that's about that. What up? Well, we already know what the chance that the test screams computer given that I'm a computer. It's a 90% success rate. So we know that the probability that it is basically this is equal to 0.5 times 0.09 or 0.9 divided by whatever this is. So we actually don't know. This is saying what is the chance that regardless of what it is, just like what is the chance that the test just screams computer, essentially. Because like think of it this way, a computer is programmed to either spit out like human or computer. So like we need to know what the chances of it actually spitting out a computer. So we actually don't know what this is. So not necessarily. This is not 0.9 because 0.9 was given that you're a computer, the chance that you scream computer is 0.9. But now I'm asking what's the chance that the test just screams computer, period. Right? Like irrespective of whether I'm a human or not. Like what's the chance that it'll scream computer at me? So technically not. So what we're going to do here is to find the probability that the test screams computer. Let's say test screams computer equals TC. We'll just say this is probability. We'll just say that just to make this easy. What we're going to need here is some set theory. The only way we're going to do this is with set theory. So what happens is this. So the probability of the test screening the computer is the probability that you get the test screens a computer and what is that? Insert equation. What is it? And MatCal U. Because what's happening is that what we're essentially doing is this is by the identity wall. What we're using is set theory walls to basically build whatever the hell that we're trying to get back to. So using this, we can say the probability here is equal to the probability of TC and either you're a computer or not a computer. This is by inverse law. So what we're saying is either in our universe, either you are a computer or not a computer at all. And so that's what this is representing. Does that make sense so far? Or not really? Yeah, what's up?
So I have a question. So the two things, we're trying to prove that our friend is a computer, right?
Given that the test screams a computer, we're trying to see, like, given that the test screams computer, what's the chance that our friend is actually a computer? Because the test could be wrong. We don't know if it's 100%. We know it's not 100% accurate.
Case is a test for that. He's a given tested wrong.
Technically not, because we don't know what he could be. We could test that he's a human and it's wrong, I guess. But like we're just using the definition of like conditional probability to try to solve it because it's, well, a conditional probability. Does that make sense? Because we have because like given that the test says it's a computer, we need to know what is the chance that your friend is actually a computer. Did the test actually get it right? Does that make sense? Or not really. So like what's happening here is that so we're just saying the chance that my friend is a computer, given that basically given that the test said my friend is a computer, I actually want to know if that test was correct or not in identifying it. So that's what this is. And then we're just trying to find the probability definitions here based off of that. This is by definition of conditional probability. By definition of conditional probability. Here. So far, so good on that fact. Okay. And so now what we have is we're just trying to find the probability that the test screens computer no matter what. So now just basically kind of like back here. And so what we have here is that this thing here is equal to the probability that we have TC intersection C plus the probability of TC and not C. This is by distribution and the fact that you can't be both a human or you can't be both a computer and a human, given that we'll just say given the fact that you can't be both a human and a computer. Basically, these probabilities are disjoint. Does that make more sense? And so now we have to calculate what this is. Okay, so we have to calculate what this is. So now what we have here is this. So the probability, this is the probability that you get TC times the probability that you get that this stuff here plus the probability that we have what is it? Oh shit. I want to reverse this. God. Oh, this was not a fun problem. TC was probability of over line, I want to say over line A. This is not a fun one. TC. This is by commutative properties, commutative loss. And so, oh my goodness, what the hell is this problem? Why is this thing? This here, okay, is the probability that we have a what is this? I don't remember off the top of my head. This is the probability that we are a computer times the probability that the test screams computer, given that we are a computer, plus the probability that we are not a computer times the probability of TC and not a computer. Okay, I think this is somewhere along the lines of where I need to be. Hopefully, this is by definition of conditional probability. Condition. Oh, no, because the events are independent of each other. Got it. Okay. Yeah, that. And so we can say is this stuff here. Oh God, this is not a fun one. Okay, this is equal to, I want to say it's 0.05 times 0.9, because that's the accuracy of the test, plus 0.95 times, what's the inaccuracy, 0.1. So, which equals the probability that the test screams computer. And so, thus, oh God, oh my God, okay. So, thus, probability that my friend is a computer, given the test says computer, is equal to basically this the 0.045 or something like that divided by this crap here, whatever that spits out. Yeah, something like that. So the reason why we did it, kind of like explaining it hopefully a bit better, is so we're trying to find like this stuff here, and that's the probability of a computer, the probability that you are a computer and the test says you're a computer divided by the probability says the test screams computer. Yeah, that's it.
So, the way I did it was kind of less, like more math.
Mhm.
But I did like, there's only 4 possible outcomes, and 2 of them are when the computer says that you're a computer.
Mhm.
So then I just took the probabilities of those 2, added them up and then divided by the probability that your friend is a computer. Like, your test is right.
What did you get end up getting?
30.45 over
0.045 divided by like 0.14 or some shit like that.
Yeah.
Yeah, that works. I'm fine with that. Basically, we just took the longhand route on this. Basically, God, this was not a fun proof that I had to do.
You know that FSM problem you've done this?
Yeah.
The summer test?
Mhm.
You do that one?
What was it even? I don't even remember. Oh, son of a bitch. Yeah, I can pull it up here. Let me pull up that thing. Give me 1 second. Hold on. Oop, no memento. I just need to pull it up. Okay. Oop. Hopefully. Oops. Let's see if I can find it. I hope I put the right one. This is going to be awkward if I didn't. Right. God, that was nice. Is it this one right here? Is it that guy?
Yeah.
Except the word join with AA. I'm gonna modify this because it would be ridiculously hard. Assume modification. Modification. Hmm?
That's,
Oh, it's because I have all the access to it.
but we don't.
Nope, because fuck you. I'll have to check with Mead and see if I can use it or if because we might use some of the test questions. But I know he's not using this one, so I'm like, okay, I'll just use this one. So assume your input space is a Z. A through Z. Okay. I want you, all right, so what are the properties, what are the things we need for a FSM? What things do we need?
Mistakes.
What's up? So we're gonna need some state spaces. What else do we need? Right, your inputs. What else do we need for it? Yep, you need, okay, you need a starting space. What else do you need? What do we call that? There's a better word that describes it. But there's a better one. What do we call an ending space? Nope. That's a space that we can stop the program.
That's great.
Nope, not called that.
Is this here?
Nope.
It's. And it's good.
It is accepting space. The accepting space. You need to know where we accept. What else do we need?
Transition.
You need your transitions. And then what else do you need? Yeah, you need your input. These are the 5 things that you're going to need for this. And now we're going to try to essentially draw this out.
So to get full points, you like me to write out those things you need?
No, but I'm helping you keep track of like what you need. So what is my what should I start to draw here?
Yeah.
Oops. What should we draw here? So like where would I start? Where would my starting space be? But I mean inputs don't sure, but like do you start with an input when you turn on the machine?
You start with the start space.
What's the start space? Identify the start space. Sure, we can call this off and modify as needed. Yeah, so remember,
Zero.
hopefully the idea is this: you don't want to have your machine on, because if you have the machine on, you might have an exploding computer. So the idea is that you always want to start your circuitry or your hardware design when the machine is shut off. Now, if I'm shut off, where do I go? Okay, let's say, all right, so obviously it's now turned on. Okay, so let's turn it on. If I turn it on now, what do I take in?
Take it input.
What does the input take? What's the, okay, what letter do I put?
Sorry, A.
Okay, where does A go? Well, yeah, but what does it go to the accepting space?
The A space.
Just goes to space A. So you would have basically, you should be going to a space that is ... A. Right? Yes, Scott. Ta-da. Yeah. already thought one step ahead, but yeah, so this is like dot dot A. Basically, you're in the middle of, you should be transitioning to a state where where the last thing the machine reads is an A. Does that make sense? Okay, now what? Yes,
Is this, sorry, I just came into it, this is damn on Discord.
yeah, no, I'll see if I can post this and then I'll let you guys try it on your own, essentially. But I'm trying the FSM question. So there's this machine, it's from transition A, we went to a state of, I guess, we'll call him dot 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 A or something like that. Actually, you know what? Fuck it. We're gonna make this just say all that. Whatever. We'll just say that this is A now. Fuck it. We'll say it's A. Okay, now what? What's another input? Another transition? Why? So remember, every input needs to be accounted for. It's like a computer needs to account for every input. What was my inputs set?
A to Z.
A to Z, right?
A to Z.
So where would B read?
Use space.
Okay,
They're trash things.
you can make a trash space if you want. I don't know. So if I put this, so you're saying if I basically put a B, you want the machine to shut off again. So I press a wrong button on here and my machine just shuts off.
No.
Well, shit, that's a shitty machine that I just got. Okay, probably not good to have a machine that shuts off if you don't hit A.
So then the area.
Sure. Okay, sure. We'll go with aerospace. Yeah, that works. Yeah, we could call it that. So,
The word has to end in AA, right?
yes, needs to.
So we can take in B, right?
What's up?
We can take in the letter B.
Yep. You can take in a little B. So this is, we'll call this error. What else? What's up? How do we do from B to Z? Well, what's the notation for B to Z? Sigma minus. What's up? Exactly. Yep. What we can say here is that this is from sigma minus space A should read you all the way to the error state. Does that make sense? Sigma is your input. So far so good on that. Now, my question is this. There are two new states, state A and state error. What do we know about, what is it about every state? Every state has to what? What does every state need to account for? So doesn't it make sense that every single time I draw a state, you keep drawing arrows out of it?
Yeah.
So how many new arrows do I need to draw? Is it 25? How many letters are there?
Or new error.
Well, technically 4 new arrows, but 2 of them are,
Error.
well, technically, but like think of those 2 arrows as like 25 of them scrunched together.
Yeah.
So like technically speaking, 52 arrows if you want to be for one for every letter that you have, right? Because like you could say this is B, then draw another arrow that's going from here to C and so on. But that's the idea. All right, so let's start with state A. If I'm at state A and I get an A, where do I go? Okay, the accepting space. What is this accepting space called?
We go.
There's a better
And
name,
we
but
should go back to the beginning.
you don't want, you would shut off the, if you go back here, you shut off the machine. Yeah, that's not a good thing.
If our starting state is off, doesn't that mean that when we start the machine turns itself off?
Well, it starts on, but we assume that when you give an input, the machine's on. We can assume that when you give us an input, you have to have a machine turn on. I don't think any computer engineer would construct a circuit where the system just shuts up. It takes an input, even shut off.
So
Sounds
our
bad.
starting space should be like empty? Do we do that?
Sure, you can make it empty. Yeah. That's better. Yeah, you can have yeah, that's a better one than just off. It's just don't put anything there, essentially.
And now we can go back to the beginning.
Technically, no, because then it has no input. Like, this is like saying it didn't end in AA, it didn't end in anything, it just off, it's just on or whatever it is,
Yeah.
the blank state.
So when it's saying, how do we know it ends with AA and AA is not in the middle, or are we just assuming
Someone's.
So you can, what we could do is we could do a modification on this. We could say, really what we could do is we could say dot, 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 A. Basically, the dot, dot, dot accounts for the fact that even if you're in the middle of a foot, like if you have like this giant word, we know it's whatever that phrase is, dot, dot, dot. But then the last two are clearly defined to be AA. Same, so we could do the same thing here.
error though? They
Yeah.
are another-
What's up?
It's like if we have A, B, A, C or whatever,
Mhm.
we have to narrow two errors.
Yeah, we would have, according to this would be an error essentially. Like if we did anything other than an A, go to an error, essentially.
You Add like another transition button for like ending, so like it can signal when the word ends.
It shouldn't know when the word, this is infinitely long, or the word. So all we need are phrases that end in AA. Like you don't need to specify how long the word is. I want that word to be as long as I want it to be. Does that make sense?
So there's no ending or there's just stop, right?
It should be like a self-contained loop, essentially. What I'm saying is like the loop should self-contain itself. Because in theory, like you could have it start, like if you enter another A, where do you think I'm gonna go back? Yeah, essentially a transition. Yeah, it goes all the way back here. Yeah, it goes right back here.
When they go back to itself, though, because then it's still have AA. and then-
AA, actually, yeah, never mind, hold on. Yeah, it should go back to itself. AA, and then if it has an error, if it's anything else, it should add an error. Yeah. And then if we're at an error, what are my transitions? Because remember, every guy needs arrows coming out of him.
So, yeah,
Where do I go?
from error to the end.
Yeah, you go here, and then if you get anything else. Yeah, you move back. What's up?
So this takes into account like the entire string, so.
The entire string.
Dot, 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 but you're just trying to check.
Yeah, I don't care how, because that's the thing with the dot, dot, dot. I don't know how long it is, and it's supposed to not care, essentially. The machine is not supposed to know until it stops inputting that. Does that make sense? So yeah, this would be an example of a FSM that checks for AA strings.
And just, this is like a pretty basic one.
Pretty straightforward. Pretty straightforward. FSMs in general aren't the worst. The hard part is just making sure that like you need to have it. Like if you can you need to identify your inputs. You need to identify your states, and then you need to identify how you go from state to state. Remember, every single state needs arrows coming out of it, and you need to account for every input. If you do not account for every input, there is something missing in your design.
So.
This is all you need to do.
Yep.
Okay.
So you pretty much like errors from ever accept, I would say the acceptance.
No, even the accepting state, needs it, because like even though like it obviously accepts, that doesn't kill the program. Accept just means good.
Oh, so yeah, it's basically there's an end spot that's like loose, like
There shouldn't be a spot where the machine just dies, essentially. I don't want my machine to die. That doesn't seem like a very efficient machine. So all I want the machine to do is keep running and just essentially keep identifying spots where the phrase is in AA or not AA. Yeah, that's where we accept, but it still keeps going, essentially.
Can you explain why we don't have a range for number one?
Yeah, I can explain. On the test, should we be defining each base before we draw the FSM? No, just draw the FSM. we can pick up on what your spaces are. E, so that's that one. Again, oh, also, just kind of like a quick note, there are multiple ways to draw in FSM. Just, like this is just one of the ways. Some of them are easier to draw, some of them are harder to draw. They all mean the same thing. Okay, so the thing that we have, what was it? Oh, it was somewhere here. Is it this guy here?
Yeah.
Okay, we'll just copy and paste and then explain this. All right, so what we have is this guy. So like the domain and the range. So yeah. So what is F supposed to be? Now, what does a function mean? Yeah, a function means every domain value, every domain value needs a codomain value, right? Well, this definition implies that every x is used, correct?
Yeah.
The problem is this. So what if my range was 3, 4, Z? 3, 4, 2, 5, A, and let's say 3. I don't know. Let's just say it's that, right? Which of these values did not get used? But guess what? Guess what? You can still make the function above. So that's why it's unknown, because if I can say that 3 could be in the range and it's not used, you could stretch that infinitely long. That's the idea with that. Any other questions that you guys have for me? Yeah, we can talk about 21. So there's a so there's this relation. So there's a reflexive relationship on this set. A is equal to 2, 3, 5, and 7. The question is how many possibilities exist? So my question is this. Shit, I really don't have a good diagram. So think of so what defines reflexive relation? And then also, what is, so let's try this. What is my domain and what is my codomain? As well.
Example? Or is that a specific?
Which one, for this one here?
Yeah.
No, it's a specific answer I'm looking for. In this question, like, what is my domain and codomain? And what's my codomain? Yeah, it's just set A. So yeah, literally set A is my domain and my codomain. Now, because it's the because if it's reflexive, a relation has to be what is called homogeneous. And homogeneous relation means that your domain and codomain are identical to each other. Does that make sense? So now we need to know what the hell does a reflexive relation mean? So what is a reflexive relation? What defines it to be either in this context or in general? I don't care, but like what does what's up?
And the equivalent,
Not equivalent.
every element has to relate to itself.
Yeah, every single element in your set needs to connect to itself. So every element needs to connect to itself. Okay, so what are the pairs that I need? Ding, ding, ding. Good. Yeah, so we know we need 2, 2, 3, 3, 5, 5, and 7, 7, right? These are required to be in the set. Whatever that is. Does that make sense? So now, what is the formal definition of a relation? I'll give you here. R has to be a subset of something. Is it just A?
Yeah.
A cross A. But we call this a Cartesian product. R needs to be a subset of a Cartesian product. In our case, this. For formal definition of relation, you need to be a subset of your sets, of the cross product between two sets, or a Cartesian product. In our case, our Cartesian product is between set A and set A. So how big, so my question is this. How big is a cross A? Yeah, the 16, right? So there's 16 potential pairs we can make, right? So there has to be 16 potential pairs we can make. 4 of them are identical pairs. Those are 2, 2, 3, 5, 5, 7, 7. Now, what does that leave me with? How many? Yeah, that leaves me with 12 pairs, all of which have non-identical coordinates. Right? Coordinates. So my question is this. What is a potential pair that we could have? Yeah, let's do 3, 2. Okay, now 3, 2 has how many options regarding with respect to our relation? What are those 2 options? Exactly. It exists or doesn't exist in the relation. What about 2, 3? Same thing. In fact, what do you think? In fact, what about the 12 remaining pairs? Yeah, the 12 remaining pairs has 2 options. In the relation or not in the relation. Right? So does picking 3, 2 impact 2, 3? No. So what kind of events are they? So what do we do with the values? What do we do with these 12 twos? Yeah, we multiply all of them. Multiply them all. So how many? So the total that we're looking for is what? There you go. The 12 total reflexive relations on this set. Just what that's supposed to be. That's supposed to be 2 to the 12. Any questions on how I made that guy?
Those are all the pairs that aren't identical. That can be.
These are all the relations that we can make that have to be reflexive. They must be reflexive.
You can do this must be on the table, right?
We could do this with the table. The table, basically where I draw it out and just kind of like show you, so like, it's not a good diagram, but like, 1, 2, 3, show. 3, and 4. So this would be like 2, 3, 5, 7, and then you would have 2 and 3, then you would have 5 and then 7. And then like the idea is that like what would this pair be right here? Like what? Yeah, 2 2, and then what would this be? 3 2, and so on and so forth. And you can use that to help like visualize how the diagram is working. Because there's 12, so there's 12 because there's only two options for only two options. That pair has to be in the relation or it cannot be in the relation.
So why don't we think about one?
What's 1/2 supposed to represent? Is there a 1/2 that's existing in here?
Okay.
Yeah, think of it like a 12 character string.
So what are we looking at?
Total number of reflexive relations on a set. So given that my set is 2 3 5 7, I want you to build a relation that is reflexive. And then keep doing that until you get through them all. That makes, okay, so that's the requirement. But what's to stop you from putting more pairs in there? So like we know that 2 2 3 3 5 5 7 7 has to be in that relation. What about everyone else?
We have to count it.
Because they have the potential of being in there. So like here's an example. So like as an example, here's a reflexive relation. Right? So you could obviously you need to have the 2 2, the 3 3, the 5 5, and the 7 7. But what's to stop me from putting more? Like 3 2. And then cut it off there. Because you're forced to have those first four pairs. Everyone else is like, kind of don't care. You can be there. You don't have to be there. Doesn't matter. Yeah. 12 is because there's 16 total pairs and there's 16 total pairs we can make. And 4 of them we already accounted for. Basically, yeah, because we already know by definition of reflexive, identical pairs are forced to be in there. Every identical pair.
Isn't this reflexive to the core?
What's up?
Isn't it like that's
Mhm.
12 of them, we know it's not.
No. 12 of them we don't know the answer to. 4 of them we know the answer to. 4 of them is automatic yeses. That's the first 4 pairs. The other 12 is we don't know, and that's what we're going to find out. Does that make sense?
But then we have to add the plus 4.
So no, not technically, because so think of it like this. So you agreed that there's 2 to the 12 for those 12 pairs, right?
Mhm.
So what about the 4 identical pairs? How many choices do they have? How many choices does 2 2 have? Yeah, 1. He's forced to be in there. What about 3 3? He's forced to be in there. In fact, all 4 pairs have one option. All 4 pairs have one option, right? And you agree that they can't impact each other. They have. So for the identical pair, pairs, we would have 1 to the 4th. Does that make sense? Because literally there's 4 pairs, one of them each with one option, right? And so what we can argue is picking the total pairs or picking the non-identical pairs does not impact the identical pairs. Does that make sense? So what we would do is multiply them together. Our actual total is just 2 to the 12th, which just stays 2 to the 12th. That's why I didn't go past that. That makes more sense.
So what about for 22, where it's antisymmetric? Is that the same concept?
Mhm. So now, so now you have to build an anti-symmetric relation, a reflexive relation, here, right? Okay. Okay, so same example. So same thing, right? So we have so we still have those 16 pairs from before. Now, how many of them are forced to be in our relation?
By that.
Of the 16 pairs, which of them are forced?
You can think about four.
They have no choice but to be in the relation.
So is that four?
Yeah, it's the four identical pairs. Make sense? The 2-2, the 3-3, the 5-5, and the 7-7. Those guys are forced to be in there because remember, it's not just a anti-symmetric, it's also reflexive. So we are required by definition of reflexive to put them in there. Does that make sense? So that leaves us with how many pairs?
12.
Now, we need to focus on what it means. We need to add on the anti-symmetric part of this definition. What does it mean to be anti-symmetric?
A relates to B and B relates to A, and A equals B.
So so either we have, so basically either we need to have A comma B or B comma A or neither of these pairs. You can't have both of them, right? So do you agree that we can't do the same technique that we did in the previous one because there's not really 12 pairs because some of them are connected to each other, right? So for example, 2-3 and 3-2 are joined at the hip. You can't just choose for 2-3 and not have that impact 3-2. Does that make sense? So the idea is to create what is called a super pair. What we're going to do to get around this is to create a super pair. Okay, so the super pair, here's an example of the super pair. An example of that would be if we had 2-3, 3, 2. Basically a coordinate of coordinates. Does that make sense? What's up? Are you sure? So think of a super pair. So think of a super pair as just a regular pair, as a regular pair. No, there's nothing different about it, minus the fact that it has coordinates in it. Now, what we're saying is this: if we have 2-3, we cannot have 3-2. If we have 3-2, we cannot have 2, 3, or we can choose to have neither of them. How many options does a super pair have then? 3. Every super pair has 3 options. Include the first coordinate, include the second coordinate, or neither of them.
Here's like a tie.
Technically speaking, don't think of it as anti-symmetric. It's just the way that we can do our regular counting techniques. Super pair is a counting technique so that we can still do like included or don't include it, like to make it as black and white as possible. Make sense?
Okay.
They're not anti-symmetric in of themselves. Does that make sense? So how many of these super pairs are there? If there's 12 regular pairs, what's up? 6. There's 6 super pairs. So how many ways can we choose for the, or how many relations? Not necessary. Sorry. How many? Yeah. How many ways to include the super pair? Because there's 12 pairs, and to make a super pair, you need two pairs. You need A, B, and its opposite. And then so there's 12 of them, so 12 divided by 2 is 6. No, you're counting each super pair as having 3 options. So we have 3 to the 6, and then we have that have the 1 to the 4th. So what is our total? Yeah, so our total is 3 to the 6 times 1 to the 4th, which is just 3 to the 6. That is how many anti-symmetric and reflexive relations I can build with this. Any questions you guys have for me? Yeah, what's up? Yes, Alex.
Well,
Well, we 12 pairs because there were 16 original pairs. 4 of them got knocked out right off the bat because we are forced to have these 4 pairs above. You are forced to have these 4 pairs above because you are making not only an anti-symmetric relation, it has to also be reflexive. By definition of reflexive, every pair needs to relate to itself. So 2, 2, 3, 3, 5, 5, and 7, 7 are automatically taken away because we know the answer is that we have to include all of them.
And the question was just asking for asymmetric and non-reflexive.
Mhm.
Then,
Or anti-symmetric and reflexive.
what was just.
So then you would have 16, so you would need to have, so 3 to the 4th, I think it's like 3 to the 10th, something along those lines. Because you would have, for the identical pairs, it would be 3 options. Well, actually, no, 2 options, sorry. So included or don't include it. Because remember, the opposite of 2, 2 is. So if I make a super pair with 2, 2 and 2, 2, it's just include 2, 2 or include 2, 2 or don't include 2, 2.
Yeah.
But 2 of those 3 options are the
It's
same.
the same exact thing. So just 2 options, not 3 options.
For the diagonal,
Yeah.
the 3 to the 6 stays put though. So you would have 2 to the 4 times 3 to the 6.
Okay.
Does that make sense?
Instead of 1 to 4 to 2.
Yeah, because with reflexive, it's you're forced.
Yes.
I think I have 7 already in my day one, but I'll repost. I can repost it later afterwards. Oh, it's in the thing. It's in my Discord.
something about this.
Of the yeah, of this one. Yeah, I went over it. I think last night.
You feel like there's like three.
Do I feel like doing 23? Is that the goddamn equivalence relation? If motherfuckers, I hate you. Motherfuckers, I hate you. Okay, so alright, so what is an equivalence relation?
Transitive, reflexive, and transitive, reflexive, and
Wait, which ones are they? So it's
symmetric.
there's transitive, symmetric, and yeah, you need to prove all of them. Does that make sense? So because we said prove, you're gonna have to prove every single one of these relations. And so that's just the god awful part about it. So each one, so basically, like kind of like basically, you need to do 3 proofs. You need to do 3 proofs within this question. Does that make sense? Because you gotta account for them. So let's try the reflexive. So what is the formal definition of reflexive? What's up?
So.
Equals each other.
Are they always equal to each other? Equals is a relation. Equals is a type of like relationship, but it's not always the case that I'm working with equality. What's another way that we could say it? What's another way that we could say the formal definition of reflexive?
For all A,
Well, remember, how can I get properties of relations? What is the criteria to be what is the criteria to have property of relations? So it's what the relation has to be, so it's with an H, homogeneous, meaning what does that mean if a relation is homogeneous? Correct, so what? It's all in one set, right? So you only need to name me one set. Is my point. What is this set called?
Yes.
Integers.
Yeah, we're working on the set of integers, right? Because that's what, well, for us, that's what we're working with, right? And so what we have here is we need that A connect, we need to have that A connects to A, right? Well, what connects these two things together? What connects these values together?
Next, please.
Yeah, how do I connect our values in this this problem?
Equals, A mod.
Yeah, you need to, in this case, for us, the connection is that A needs to be congruent to A mod 4. Does that make sense? You need to prove this. This now turns into a unit 2 proof. Does that make sense?
But I can say you can put A mod one instead of B.
Because you would need to have A comma A in instead R, right? Wherever you see a B, replace it with A,
Oh,
quote unquote. Make sense? So you would need to prove the reflexive. What would the symmetric look like in terms of like what you're trying to prove? Yep. So okay, so what in this context? So in general, what does it mean to be symmetric?
You can like flip values.
Yeah, we can essentially like flip the values, right? So what we say is that for all A, B in your set A, if we have A comma B, that means we have B comma A. Right? Well, my question is, what is that in the context of this question? In our context, what is big A? What set of values am I pulling from? Mhm. Yeah, it is integers. It would be just this guy right here. Okay, so what does A or B mean? How do we define that? What's the requirement to get into a set R? Is it that A equals B? That doesn't work like an equal sign. What's that triple equal sign?
that's actually clear. I don't know what's going on.
It's a unit 2. I'll give you a hint. It's a unit 2 thing. Some goddamn unit 2 concept. What's up? No. What's this? What's this? How do I read this statement here? Yeah. A or B means that A needs to be congruent to B mod 4. Does that make sense? So if we know that A or B means that, B or A means B is congruent to A mod 4. Now prove it formally.
Okay, assume the able to, and then you just state that properties of mod.
Nope.
No, like immutable property of mod, I don't know what it's.
Nope.
I mean, that's just like, by definition.
No properties, damn it.
No.
None. None whatsoever. Go the wrong way. That implies B is congruent to A.
You just assume, and you just do QED, that doesn't make this a thing.
How do you know that? How do you know that? I'm not letting you get away with that. And then do the wild transitive. What does transitive say?
A relation B and B relation C implies A relation C.
For all A, B, C in the set of A, big A or B, and B or C implies A or C. That makes sense? So now, just like we did with all the other ones, translate essentially you in this context, what does that mean here? In this context, what are we proving? How do I rewrite this to be something similar to this? Think of what A is and think of how I can rewrite A or B, B or C, and A or C.
You know, the eighty, the student to be like, and
So A is congruent to, shit, come back here. A is congruent to B mod 4 and implies what? Yeah, you're gonna have to do all 3 of these proofs. Every single one of them. And what is big A supposed to be? Yeah, big A is the set of integers. All 3 proofs must be done to do the equivalence.
curious, what do you go about in this method? I have no clue.
What's up?
I think a lot of people are in this method one, now it's like,
Remember, there's typically with a mod proof, there's 4 steps. Definition of mod, definition of divides, a bunch of math, and then unwind the steps.
okay, so you just follow that.
Quite literally, yes. And repeat, wash, rinse, and repeat.
Okay, thank you.
Do all 4 of these proofs. Okay. Any other questions you guys have for me? I probably have to cut the stream off because otherwise I think I'm going to kill my computer. I think I've been running this for 2.5 hours and I'm not looking forward to having to upload this because I know it's going to take forever, but it's okay. Yeah.
So you can provide it like later.
Yeah, I'll see if I can be in the library a little bit. I'll upload this and then I'll also be on tonight as well. So yeah.
What time is it tonight?
What time am I gonna be on tonight? 7 or something like that, hopefully. I'm probably just going to get some food first. What's up?
You said you're coming back to the library.
I will try to come back to the library and then at like 9, I'll hop onto Discord.
When are you going to London?
Probably after I get food, depends on if I clash. Yeah, I'll try to see if I get to the library
Another day?
tomorrow for sure.
Tomorrow? Okay, because I'm not going to the library today.
No worries. That's all I have. Take care, guys.
I gotta buy